In today's video, we're going to be looking at exponents. So our vocabulary here says an exponent is a number which tells us how many times to multiply a different number, which we call a base, to itself. And the base is the number that's being multiplied. Bases and exponents are written with the base looking like a normal number and the exponent looks like a superscript or a smaller version of the number to the upper right side of the base. The example I have here shows us 3 to the 5th power. The base is 3, the exponent is 5. That 5 tells me that I should have 5 copies of 3 to multiply together. And you can see when this is expanded out as 3 times 3 times 3 times 3 times 3, we are breaking a rule from earlier about using an x as a multiplication symbol. This is one of the few times that we will dispense with that rule. And like most rules, there's always a place where it isn't the most useful to us. Exponents is one of the instances where an x is still absolutely fine for multiplication. Quick note about wording. If we have an exponent of 2, instead of saying 3 to the 2nd power, we might say 3 squared. And if we have something that has a power of 3, 3 to the 3rd power, we may say 3 cubed instead of 3 to the 3rd power. Mathematicians just understand that squared means power is 2, and cubed means power is 3. So our first two examples ask us to write out, using multiplication, these two exponents, and then determine what their actual value is. So we start with 4 to the 5th power. Well, 4 to the 5th power means I'm supposed to have 5 4s. The exponent of 5 says I should have 5 copies of the base, and the base is 4. Now, when it comes to multiplication, we can only do pairs. So 4 times 4 is 16. The third and fourth 4, 4 times 4 is 16. And this 4 in the end is still just a 4. And everybody here is still multiplied. Multiplication, again, only two things at a time. So 16 times 16 is 256. And this 4 on the end still doesn't have anybody to work with. And now we just have 256 times 4. Probably don't know that off the top of our heads, and that's okay. We just have to go to the side, or in this case on the video here, I'm going to go above, and work it out. So 4 times 6 is 24, carry our 2. 4 times 5 is 20, with the 2 makes 22, so we both write and carry a 2. 4 times 2 is 8, 8 plus the 2 we carried is 10. So 4 to the 5th power, expanded, is 4 times 4 times 4 times 4 times 4, and the actual value of 4 to the 5th power is 1024. We're also asked to write out with multiplication and determine the value of 7 cubed. So let's see. The exponent is 3, which means I have 3 copies of the base. The base is the 7. Again, multiplication, we can only multiply two things at a time. 7 times 7 is 49. And this third 7 is along for the ride. Now we have a multiplication statement of 49 times 7. Again, might not know that off the top of your head, so we can do it on the side. 7 times 9 is 63, carry our 6. 7 times 4 is 28. 28 plus the 6 that we carried is 34. So 49 times 7, and ultimately 7 to the 3rd power, is 343. Another type of problem that we will encounter asks us to write 64 using 4 as the base, meaning we're going to write 4 to a power. We just don't know the power. Alternatively, if you're thinking about this with symbols, you might think about it as 4 to the we don't know equals 64. Well, exponents are just repeated multiplication, and my base is 4, which means the only number that I'm allowed to use is 4. You'll have to pardon my dog. I'm recording these in summer. My mail was just delivered, and my dog had to let the mailman know that he needed to get off the porch. Back to math. The question is, strictly using 4s, how many times would I need to multiply to get 64? So, 4 times 4 is 16. That's not 64. The only thing I'm allowed to do is multiply by 4, so I'm going to do it again. 16 times 4. Ugh. Let's write that a little bit nicer. That way, if anybody ever pauses the video, they can actually understand what I wrote. 16 times 4, we can break that up as 4 times 10 is 40. 4 times 6 is 24. And 40 plus 24 is 64. There's my 64 that I'm looking for. It required 1, 2, 3 4s. So 64, with 4 as the base, is 4 to the third power. The next batch of examples, nice and easy. Write in exponent form. We're not trying to figure out the value. We're just going to write the base with a power. All you have to do is count. How many 3's are in this first example? 1, 2, 3, 4, 5, and 6. So we have 3 to the 6th power. That's it. In the second example, we have 1, 2, 3, 4's. So we have 4 being raised to the 4th power. In the last example, we have 3 2's, so we have 2 being raised to the 3rd power. More examples. Determine the exponent needed to make the statement true. Hey, these look like a previous example. Write 64 using 4 as the base. This is just a different way of wording it. 3 to what power will make 27? So the question is, just using 3's, how many would I need if I'm just multiplying and I'm trying to make 27? Well, we start with 3 times 3. That's always going to be the first step, the base times itself. That is 9, and 9 is not our target. We're looking for 27. So we need to multiply by another 3. 9 times 3 is 27, and that's our target. It took us 1, 2, 3 3's to get there, so 27 is 3 to the 3rd power. For 5 to an unknown power equals 625. Again, same idea. We're going to multiply together a bunch of 5's until we land on 625. So 5 times 5 is 25, not the target. So we'll multiply by 5 again. 5 25's is 125. Still not the target. We'll multiply by 5 again. 5 times 100 is 500. 5 times 25 is 125. And 500 plus 125 is 625, which is what we're looking to make. So what did we need to do to make that? We had to use 1, 2, 3, 4 5's. So our exponential version of this is 5 to the 4th power. A quick special note, which will come up later in the year as well. Any base that has an exponent of 0 to the 0 power has a value of 1. The only exception to this rule, because most rules do have exceptions, is the number 0 itself. 0 to any power is 0. The last thing I'm going to ask you to do with exponents is deal with this type of problem. You can read this. We use a system of tens to identify numbers. Ones place, tens place, hundreds place, thousands place. Well, ones place can be described as a number of 10 to the zeros, because 10 to the 0 is 1. And the tens place can be described as a number of 10 to the first powers, because 10 to the first power is 10. The hundreds place can be described as 10 to the second power, because 10 to the second power is 100. Thousands place by 10 to the third, and so on and so on. If we needed 10,000s, we could do 10 to the fourth. 100,000s could be 10 to the fifth. Millions would be 10 to the sixth, and we could keep going. I'm not going to ask you to do numbers quite that big. Last thing I want you to do is to write out a number using powers of 10 and exponents. This is going to feature a lot of work with parentheses as well. In this number, 2,456, we have a 2 in the thousands place. When we write this out in expanded form, okay, when you were first introduced to expanded form, you would have written 2 times 1,000. And then you would have written 4 times 100, 5 times 10, 6 times 1. That's expanded form, and that's how you were introduced to the powers of 10. But now, in pre-algebra, we actually use the powers of 10. And instead of just writing this list, we're going to write it with addition signs in between. What I mean, so 2 times 1,000 is going to look like 2 times 10 to the third. That's 2 times 1,000. We need to add on our 4 times 100, which is going to look like 4 times 10 to the second. Add on 5 times 10 to the first. Add on 6 times 10 to the 0. Notice each place value is in its own set of parentheses in this expanded form, and that we do have the addition shown in between.